Good afternoon. Today I'm going to be talking about implementing imaginary elementary mathematical functions in Chapel. Let's talk about multiples of the square root of -1 or I to its friends. These are what since the 1920s have been called imaginary numbers. Chapel supports them with a primitive or base floating point type. This is the parameterized type imag.w. Chapel is one of the few high-performance computing compiled languages to do so. C, D and Ada are the others. Okay, elementary mathematical functions. These exist for real and complex arguments, but no such functions exist for imaginary arguments. If they did exist, many would return an imaginary result. Some would return a complex result. A few would return a real result. Consider the square root of an imaginary number, square root plus or minus yi, where y is non-negative. We call y the multiplier. The result is just s plus or minus si, where s is equal to the square root of a half y. It is a complex number, but the only serious computation is just a single real square root evaluation, and there is no complex arithmetic. Let's rewrite the polynomial form of a complex number z equals x plus yi in polar form. X plus yi equals r e to the I theta, where r and theta are the magnitude and phase of z, and e to the I theta equals cos theta plus I sine theta. Making x 0, so we restrict ourselves to imaginary numbers. For the magnitude, we use Chapel's sign bit operation abs. The phase is a compile time constant for non-zero y, and the phase is just y for 0y, or y being not a number. Again, a real result needing no complex arithmetic. And then we have the imaginary exponential and imaginary logarithm. While they both return a complex result, they involve no complex arithmetic. They are computed solely from functions returning real results. The sine and cosine in the first case, and the logarithm and phase in the second case. Let's look at implementations of the routines mentioned so far. The square root's pretty simple. Grab the multiplier, compute the square root of half of that, deduce the sign of the imaginary component, and use a custom coercion routine to build a complex result from the real and imaginary components. The phase is even simpler. Look at the multiplier and return a real result, either an appropriately signed real compile time constant, depending on the sign of the multiplier, or just the multiplier itself. Note the compile time pix routine, which returns a correctly typed value of pi times 1/2. The exponential reads exactly like its formula, returning a complex number, and the logarithm also reads exactly like its formula, again returning a complex number. Let's move on, the trigonometrics. These are still quite simple formulae. The first returns a real result, the second last a complex result. Those in between return imaginary results. That inverse hyperbolic tangent in the final case for a real argument is problematic. Only over the very limited domain of -1 to +1 does it return an imaginary result. Outside this domain, it returns an imaginary, not a number. Not very useful in practice. Do we force this routine to return only imaginary results? Team discussion went back and forth over email many times. We really wanted the function defined for any imaginary argument, so we coerced yi to complex and reverted to the inverse complex tangent. The implementations are all pretty simple. Most of them are one-liners. Notice that last case we're returning the complex inverse tangent, and in the second last case we're also reusing that compile time procedure pix, which returns an appropriately typed value of pi times 1/2.
More of the same. Well, almost. The hyperbolics. The result of the first is real, that of the second last is complex. The second, third and last cases are imaginary. The fourth case uses an inverse sign for a real argument. It's problematic. Only over the very limited domain of -1 to +1 does it return a truly useful result. Anything outside this domain is an imaginary, not a number. Sound familiar? Same discussion cycle, same requirement, same conclusion. So we coerced YI complex and reverted to the inverse complex hyperbolic sign.
And the implementations are, again, pretty simple. Notice that fourth routine, which returns a complex result. The fifth case, the inverse cosh, has some slightly hairy mathematics. We ran numerous test cases. Runtimes were normalized with respect to a reference case and then compared. That reference was the function with a real argument returning a real result. The identical function, but with an imaginary argument returning an imaginary result, runs in much the same time as the reference case and about half the time of the complex variant. In other words, with a complex argument and returning a complex result. The gains were as expected, because most formulae with an imaginary argument call only real functions. Success. We now have imaginary elementary functions for Chapel. Implementations are complete and consistent for all floating point types. The detail was straightforward once we sorted out the mathematics. The mathematics mostly involve nothing more than real functions. These new routines perform well and gave us the performance we expected. These functions did all the special case handling for us. Chapel easily handled generic arguments. Euler's formula, however, highlights a need to rework cos and sine at some stage.
Yeah, I have a question for Damian. Damian, it sounds like you may have done this kind of work in a different language, or maybe several different languages before, implementing or extending arithmetic and support for functions and so on. How does Chapel compare with other languages that you've tried this in?
It's actually in no other language, in the sense that it's been part of the C standard since C99, but nobody's implemented it. And I did this in Chapel because Chapel had a full implementation of imaginary arithmetic, which means that it was possible to actually implement this. I didn't attempt to implement it in any other languages. And as I said, the only other languages where you'd stand a chance of doing this would be C, D, or Ada. The only compilers that I know of that I've got access to that have got imaginary types of D and Ada, and I didn't get around to implementing it in either of those two because I'm not terribly interested in those two. But technically it's in the C standard, but there are no current C compilers out there that implement imaginary arithmetic for starters. So, yeah.
I see. So C is sort of in the too hard basket, and Chapel made it easy. Yeah, thanks.
Yes, Chapel made it easy, and it worked, and everything worked as it was predicted. And I apologise, there's some typos, and I have no idea why in that presentation. everywhere where I had a question mark W in the argument list, my cutting and pasting from my paper, I've somehow lost all of those question marks in the argument lists. I will go back and correct that so that the PDF version that it'll be up on the website will have all the question marks in there. Sorry about that. Oops.
Thank you so much. I see another question in the chat box from Luca. It's he's saying, very cool. Are these in Chapel code base already? If not, any plan to integrate them?
Yeah, Jade might be better. Jade, I think, was putting those bits and pieces in there. It's not directly out of all the work I've done, because the work, but we had a GitHub conversation going, so I was passing information over to Jade. It's not in. I don't know, Jade, is it? If you grab the current nightly release, is it in there yet?
Yes. So for the trigonometric and hyperbolic functions, this is implemented in the standard library on main today, with the exception of, I believe it's assigned. There's two of those functions that are not, because of that limited domain that Damian mentioned. And so the standard library has the correct implementation for all range of numbers, rather than the performant implementation for a smaller range of numbers.
Perfect. Thank you.